This is Algebra 2, Lesson 8-3, Rational Functions and Their Graphs. A rational function is a function that can be written as f of x equals p of x over q of x, where p of x and q of x are polynomial functions, and q of x cannot equal 0. The domain of f of x is all real numbers except which values would change q of x equal 0. Here I have 3 examples of rational functions. And we have y equals negative 2x over x squared plus 1, which looks like the graph that you see there. We have y equals 1 over x squared minus 4, and there's its subsequent graph. And then we have y equals x plus 2 times x minus 1 all over x plus 1, and there's the graph of that equation. Now, in the first rational function, the y equals negative 2x over x squared plus 1. If we look at the denominator, there is no value of x that would make the denominator 0. Okay, because even if I put in a 0, 0 squared is 0, 0 plus 1 is still 1. So there's no value of x that's going to make the denominator 0. So the graph is considered to be what we call continuous, because it has no jumps or breaks or holes in it. So in other words, if I put my pencil down on my graph and I just trace my graph just like this, I'd never need to pick my pencil up. Okay? In the second graph, however, it's a rational function, but we know that if we factor the denominator, x squared minus 4, we factor that to x plus 2 and x minus 2, and then set that equal to 0. We know that if x equals 2, 2 squared is 4, and 4 minus 4 is 0. If x equals negative 2, negative 2 squared is positive 4, and positive 4 minus 4 is 0. So that makes the graph what we call discontinuous, because I would have to pick my pencil up. I can graph this part, have to pick my pencil up to graph this part, have to pick my pencil up again to graph this third part right here. Same with the last graph. I can graph this section, but I have to pick my pencil up to graph this section. So the last 2 graphs are what we would consider to be non-continuous graphs. Okay? They're not continuous. They're discontinuous graphs. Now, if a is a real number for which the denominator of the rational function f of x is 0, then a cannot be in the domain. The graph of f of x is not continuous at x equals a, and the function has a point of discontinuity, which is what I just discussed with you. All right, so let's continue on here for just a second. This is kind of interesting. It's a little bit hard to understand until you actually do some examples, but just bear with me, it will make sense. A point of discontinuity is removable if the function can be redefined at that point to make the function continuous. That happens when there are common factors in the numerator and the denominator. As we see here in this problem right here, we have an x plus 2 in the numerator and an x plus 2 in the denominator, which means technically if we simplify this equation, those 2 sections would cancel out, because the only time we can simplify is if you simplify exactly the same factors that are multiplied together. So that means that this has a removable discontinuity at x equaling negative 2, because if we solve the denominator x plus 2 equals 0, x would equal negative 2. Okay? This creates what we call a hole in our graph, and it's called a removable discontinuity, because you can make the function continuous by canceling out both the x plus 2 parts. A point of discontinuity is non-removable if the function cannot be redefined at that point. So when you are looking at discontinuities, it's helpful to factor the numerator and the denominator as a first step. The factors of the denominator will reveal the points of discontinuity, and the discontinuity caused by x minus a to the n power in the denominator is removable if the numerator also has an x minus a to the n power as a factor. So, all that being said, how do we find points of discontinuity? That's what we're going to look at. So, if I give you the following rational function, y equals x squared plus x minus 6 divided by 3x squared minus 2. First thing we're going to do is factor the numerator and the denominator. So if I look at my numerator, I have x squared plus x minus 6 over 3x squared minus 12. So if I factor my numerator, I need 2 numbers that multiply together to get negative 6, add together to get positive 1, so it's going to be x plus 5 and x minus 1, so negative, it's going to be x minus 1. That's going to factor to x plus 3 times x minus 2. Something like that. X plus 3 times x minus 2, because negative 2 times positive 3 is negative 6, but positive 3 times plus negative 2 equals positive 1. The denominator will factor out. First, I can take out a 3 here, and I'm going to get x squared minus 4, and that's a perfect square, the difference of a square. So that becomes 3 parentheses x plus 2 times x minus 2. Hopefully you remember your factoring. We've done it quite a bit this year, a lot when we were in Algebra 1. Now, if we look at this, we could simplify this, because if I look at this now, I can say, oh, look, this x plus minus 2 and this x minus 2 will cancel out. So simplified, this equation becomes y equals x plus 3 on the top over 3 times x plus 2 on the bottom. Okay? Which means now I can look for things. Look for values that are zeros in both the numerator and the denominator. Okay? So if I look at that, I have a common, I have the x minus 2 and the x minus 2, which I canceled out. Which means those will both, they'll be, that will give me a whole. Right? So because those are the same things that I multiplied together, those are the same factors. Since I factored out x minus 2 and x minus 2 in both cases, x minus 2 equals 0, so x equals 2 is a point of discontinuity that is removable. Okay? This is a removable discontinuity. Okay? So we call that removable discontinuity a whole. Now, we're going to look at for the values that are zeros at the denominator only. If I do that, I have an x plus 2 left over, don't I? So I have x plus 2 equals 0, so x equals negative 2. This becomes, okay, this becomes a 0 in the denominator only, which means that this gives us a vertical asymptote at x equals negative 2. Okay? So this gives us a vertical asymptote at x equals negative 2. So if it can be removed, it's a removable discontinuity and is considered to be a whole. If it cannot be removed, and we're talking about the denominator only right now, then it becomes a vertical asymptote. You set that equation equal to 0, and that becomes your vertical asymptote. Then the last thing you can do is you can compare the degree of the numerator and the denominator. Remember, in this equation, I had, original equation was y equals x squared plus x minus 6 over 3x squared minus 12. Remember, we have the top equation is a quadratic equation, the bottom equation is a quadratic equation. So we have the a and the b and the c value. So we're going to compare the degrees of the numerator and the denominator. If the degrees are the same, right? If the degrees are the same, then we end up with a horizontal asymptote. And we have a horizontal asymptote. I'm going to discuss this a little bit further. I'm just introducing it to you right now. Since I have a degree of a power of 2 here, I have a degree of a power of 2 here. The degrees are the same, which means I have a horizontal asymptote. I have a horizontal asymptote at the point where y equals a over b, where a is the leading coefficient of my numerator and b is the leading coefficient of my denominator. Okay? So the leading coefficient of my numerator is a 1, because there's a 1 in front of that x squared. The leading coefficient of my denominator is a 3, because there's a 3 in front of the x squared on the bottom. So I have a horizontal asymptote at y equals 1/3. And I'm going to sum all this up for you in just a few minutes, and it'll make a lot of sense. So, and this is the wrong direction, so scribble that out. Don't know what I was thinking when I typed this. We're going to look for the domain. Oops, that's the right direction. Yours is the wrong direction. You need to scribble yours out and write this in. I fixed it on the smartphone. Okay? So you need to write in the directions that I did here, which is find the domain, the points of discontinuity, and determine if they're removable or not removable, and the x and y axis. We'll talk about asymptotes in a little bit. Original directions were to find the asymptotes and vertical asymptotes and horizontal asymptotes, which until I really teach you how they work, That doesn't work. I put the wrong direction in there. So this is the correct direction. Find the domain, the points of discontinuity, and determine if they're removable or non-removable. And then find the x and y intercepts of each rational function. So, to find the domain, okay, first thing I'm going to do is I'm going to factor it, which means this will factor to x over x plus 3 times x minus 3. Okay? So it has x plus 3 over x minus 3, which means that, okay, it is undefined. I'll have a 0 in the denominator. It's undefined at x equaling negative 3 and x equaling 3. Okay, which means my domain is all real numbers except where x equals 3 and negative 3. So my domain then is all real numbers except x equaling 3 and x equaling negative 3. So there's my domain. I've done that. Now I need to find my points of discontinuity. Okay? So the discontinuity is where I would end up having a 0 in my denominator. So my points of, I have discontinuity, and it's non-removable because there's nothing on the top that cancels to the bottom. I have non-removable discontinuity at x equaling negative 3 and x equaling positive 3. And now to find my x-intercept, the x-intercept is where the numerator equals 0. Okay? My x-intercept is where the numerator equals 0. And the only time that the numerator can equal 0 is when x equals 0. If x equals 0, then the numerator can equal 0, so my x-intercept is x equals 0. To find the y-intercept, you let x equal 0 and solve it. So to find my y-intercept, I'm going to look at this equation here, and I'm going to let x equal 0, and I'm going to solve this equation. So if I want to do that, I'm going to have y equals 0 divided by 0 minus 9, which is still 0. Okay? So my y-intercept is 0. So my x-intercept is 0, 0, and my y-intercept is 0. Now let's look at the second one. Again, start off by factoring. So I'm going to take the 6 out of this, and I'm going to end up with x squared minus 1, which will factor again to 6 times x plus 1 times x minus 1. And in the denominator, I just have the x minus 1. So if you can see this, you can see that we can cancel out this and this right here, which means I have two things I need to pay attention to. It is undefined at x equals 1, because I'm looking at my denominator, so I'm going to look for my domain first. It's undefined at x equals 1. At x equals 1. So, the domain is all real numbers except x equaling 1. That's where it will make it undefined. Okay. Since y equals 6 parentheses x plus 1, when it's simplified, except at x equals 1, we have a removable discontinuity because we could remove it. Notice how I canceled it out? That means I can remove it. If you can cancel it out, that means you're removing it. So I have removable discontinuity. At x equals 1. You solve that thing. Okay? Which means that's a hole at x equals 1. Removable discontinuity at x equals 1 means I have a hole there. So if it was a straight line graph, it would go like this. There'd be a hole in a straight line graph. And that's all it means. Okay? So now we need to find the x-intercept and the y-intercept. The x-intercept is when the numerator equals 0. Okay? So if I look at this, my x-intercept occurs when my numerator is 0. So if I look at this, okay, and I'm going back to my original equation, how do I get my numerator to be 0? Okay, if I put in an x equals 1, And all I have to do is, to get my numerator of 0, if I have 6 parentheses x plus 1 parentheses x minus 1 over x minus 1, to get my numerator to be 0, I either need to get this factor to be 0 or this factor to be 0, because anything times 0 is 0. So in other words, my intercept, my x-intercept is going to occur at -1 and +1. Okay, so my x-intercept is at x equaling 1 and x equaling -1. So as a point, those are, point for the x-intercept is going to be 1, 0, and -1, 0. For my y-intercept, it's when x equals 0. My y-intercept is when x equals 0, so I'm going to have 6 times 1 times -1 over -1. So I'm going to have -6 over -1, which is going to give me just 6. So my y-intercept is going to be 0, 6. So there we found our domain. We determined if we had any discontinuity, if it was removable or not, and we solved for our x and y intercepts. Now, in Chapter 7, you learned that an asymptote is a line that the graph approaches as x or y increases in absolute value. If a rational function has a non-removable discontinuity at x equals a, then the graph of the rational function will have a vertical asymptote at x equals a. That's right here. Right? So if it has non-removable discontinuity at x equals a, the graph has a vertical asymptote at x equals a. So to find vertical asymptotes, you simply look at the denominator and look at the numerator and see if any of the factors cancel out. If they cancel out, then that's not going to become an asymptote, it's going to become a hole. If they don't cancel out, that's going to become an asymptote. So if I look at this first graph here, y equals x minus 2 over x minus 1 times x plus 3. If I set, since x minus 1 equals 0, x plus 3 equals 0, if I set those equal to 0, x will equal 1, x will equal -3. Okay? Those will give me zeros in the denominator. And neither of those is a 0 in the numerator. Therefore, we have a vertical asymptote at x equals 1 and x equals -3. So I have two vertical asymptotes. They are x equals 1 and x equals -3. Looking at this second problem, I have x squared minus 1 over x plus 1. Factor it first, it's because x plus 1 over times x minus 1 all over x plus 1. So I have a removable discontinuity right there. There's my removable discontinuity. Since x minus 1 is removable, and I don't have another something in the denominator, there is no vertical asymptote here. Since there's no other numbers in the denominator, no other variables in the denominator, right? Since x equals -1 is removable, there is no vertical asymptote. While the graph of a rational function can have any number of vertical asymptotes, it can have no more than one horizontal asymptote. Okay? Magic number. Can't have more than one. It'll either have none or it'll have one. It won't have more than one. It can have a myriad of verticals, but only one horizontal. So, key concepts here. Let's review. A continuous graph, like x squared over x squared plus 1. There's no value that I can put in for x that will make the denominator equal to 0. So it's continuous. Straight line, curved line, doesn't matter. I don't have to pick up my pencil to finish the graph. A discontinuous graph can have a removable discontinuity. For example, x plus 2 times x plus 3 over x plus 2. This causes the removable discontinuity right here at x plus 2. That would be removed, and that's called a hole. Non-removable discontinuity, for example, x plus 2 times x plus 3 all over x plus 4. Nothing gets removed. Therefore, the vertical asymptote then would be where x equals 0 when you solve x plus 4. So the vertical asymptote here is where the denominator equals 0, so x plus 4 equals 0, which would be x equals -4. It's possible to have several vertical asymptotes. That's why you need to factor. Horizontal asymptotes. rules, things to check. This is the one where it's a little bit fishy and hairy for some people. If p of x is a function in the numerator, and q of x is a function in the denominator, and m and n are the degrees of those polynomial functions, m is the degree of the numerator, n is the degree of the denominator, then if m is less than n, for example, we have x plus 2 over x squared plus 2x minus 3. Notice the degree here is 1. Okay? This has a degree of 1 because the leading term, okay, is 1. Here this has a degree of 2. So that means that m is less than n, because the degree here is 1, the degree at the bottom is 2. Then the graph has a horizontal asymptote at y equals 0. If m is greater than n, notice on the second one, I have a degree of 2. This is a degree of 1. 2 is greater than 1. If the numerator has a higher degree than the denominator, there will not be a horizontal asymptote. Last but not least, if m equals n, then the graph has a horizontal asymptote at y equals a over b, where a is the coefficient of the greatest degree in the numerator, and b is the coefficient of the term of the greatest degree in the denominator, which is why you always want to put things in standard form. So if you put them in standard form, then the degrees, they're in descending order of degree. So this would be my A, this would be my B, so my horizontal asymptote would be y equals 3/2. And there is such a thing called an oblique asymptote. I'm going to introduce it, you do not have to do it, but you need to at least hear about it so that if you hear it in further classes, you'll know what it means. Like with the horizontal asymptotes, oblique asymptotes occur when the m is 1 degree greater than n. Okay, you can find the line of an oblique asymptote by dividing the numerator by the denominator. In this case, I would do long division, and it would work just fine. All right, so finding horizontal asymptotes. Remember, horizontal asymptotes all deal with m and n. Okay, and m is the degree of my numerator, and n is the degree of my denominator. M is the degree of the top, n is the degree of the bottom. Okay? So if I look at this problem, I have m equals a degree of 1 and n equals a degree of 1. So m equals n. Because the leading coefficient here is, okay, both of those have an implied 1 as a degree. Okay? Since they are equal to each other, then we have to look at the leading coefficients. Leading coefficient of my numerator is -2. Leading coefficient of my denominator is 1. Remember, the number in front of the variable is implied to be a 1. So my horizontal asymptote then will be the line of y equals a over b, so -2 over 1, or y equals -2. In the second equation, I have x minus 1 over x squared plus 4x plus 4. It's in standard form. The degree of the top is 1, it's linear. The degree of the bottom is 2, it's quadratic. Since m is less than n, according to the rules, if m is less than n, we have a horizontal asymptote at y equals 0. My horizontal asymptote here is y equals 0. Okay. This third one, my top polynomial is a quadratic because it has a degree of 2. My bottom polynomial is linear, it has a degree of 1. So here, m is greater than n. Whenever m is greater than n, you have no horizontal asymptote. Now, you can get a reasonable graph or a rational function by finding all of the intercepts and asymptotes. And then obviously sometimes you're going to have to plot a few more points. Now, I know you can put these on your calculator, but you do need to learn how to do these by hand, because eventually you will have to do them by hand. You will have to graph at least one for me by hand on a quiz, and I'm sure in other classes you will have to graph them by hand as well, so you might as well get used to doing them. So here's my graph. What is the graph of the rational function y equals x plus 3 over x squared minus 6x plus r? First things to do, find the asymptotes if they exist. So find the horizontal asymptote. That's the thing we just did. The degree of the top is 1. The degree of the bottom is 2. N is less than n. So I have a horizontal asymptote at y equals 0. And I'm going to come back to this in a little bit because I got to tell you something about this particular graph that's quite interesting. Step 2, find the vertical asymptote or asymptotes. Remember, you only have one horizontal, but you can have a lot of vertical asymptotes. Find the vertical asymptote, I have to factor it. I have to set my denominator equal to 0 and solve it. So in my original equation, I have x plus 3 over x squared minus 6x plus 5. So x squared minus 6x plus 5 has got to be set equal to 0. And so to do that, I have to factor it. So in this case, it's going to be x minus 5, x minus 1. X minus 5, x minus 1. That will give me a product of 5 and a sum of negative 6. So x can equal 5 and 1. Right? So my vertical asymptotes then are going to be x equals 5, x equals 1. So I have two vertical asymptotes. Now I'd like to find the intercepts. To find the x-intercept or intercepts, you set the numerator equal to 0. And so in my original equation up here, I have x plus 3. And I'm going to rewrite this over here. X plus 3 over x squared minus 6x plus 5. So that's my original equation. So I set my numerator equal to 0. So x plus 3 equals 0, so x equals negative 3. So my x-intercept then, right, x-intercept happens to be negative 3, 0. But if you're paying attention to anything, it says I have a horizontal asymptote at y equals 0. So why can I have an intercept at negative 3, 0? Okay, kind of interesting anomaly we have all of a sudden, because I'm not supposed to, an asymptote means my graph approaches that line but never touches that line. But this seems to contradict it, and we'll talk about how it contradicts it in just a minute. But that's where our little bit of a contradiction applies, because this is a special type of graph. Now I need to find my y-intercepts. My y-intercepts are when you let x equals 0 and solve the line. Oops, solve that. So I have y equals 0 plus 3 over 0 squared minus 6 times 0 minus 6 times 0 plus 5. So that gives me 3 over 5. Right? So my y-intercept is 0 3/5. There's my y-intercept. So I have found my intercepts and I have found my asymptotes. So the first thing I'm going to do is up here, I'm going to graph my asymptotes. My asymptote, I have a horizontal asymptote of y equals 0, so I'm just going to draw a nice thick line there so that I remember in my brain that that's a horizontal asymptote. Okay? Then I have a vertical asymptote at x equals 1, x equals 5. So there's my asymptotes, which means I could have graphs in 6 different places. So 3 down here below my horizontal asymptote, 3 above it. I've got to figure out where they go. Part of it is graphing my intercepts. My intercept was negative 3, 0. So there's an intercept there. And then my vertical asymptote was 0 3/5. 0 3/5. So I'm looking at it going, well, that doesn't tell me much about, except for this graph right here. That kind of gives me the idea that my graph would be like this in this section. Okay, but I don't have the slightest clue what the graphs are doing in the other sections. So this is where I have to place some points. So I'm just going to plot some points here, and then we're going to graph them. So if I have the function of x plus 3 over x minus 5, parentheses, x minus 1, and I'm just going to pick some points. Okay, so for the middle, I know my middle has to be between these two vertical asymptotes. So I know I have to pick points that are greater than 1, but less than 5. So I'm going to pick a point like 3, and maybe 4, because that will give me, I just need to pick 2, because that tells me where my graph's going to go. Okay, 3 or 4 of them. And so if I have an x and y for my middle 4, I'm going to pick the points 3 and 4. And if I put 3 in here, I'm going to get 9 over 3 minus 5 is negative 2, and 3 minus, I'm going to get 3 over 2, because it's going to become 6 over negative 4, which is negative 3 over 2, which is negative 1.5. If I put 4 in for x, I'm going to have 7 as my numerator, and my denominator, I'm going to have a negative 1 times 3. So that's going to be negative 3. So that's going to be negative 2 1/3. So if I look at this, okay, I've got 3, negative 1.5, and 4, negative 2 1/3. So 3, 3, negative 2.5 is here. And I've got 4, negative 2 1/3, negative 2 1/3. So I could be having a line that would go across, but I have a horizontal asymptote, so I know it can't go above the y-axis. So I know I've got to have a graph that looks something like this. So something more of a parabolic graph. It's not perfect, we're just sketching the graph. So there we go. So there's the middle section. To find the right-hand section, I need numbers that are bigger than 5. So I'm going to choose some values that are larger than 5 now. So I'm going to choose some values like, let's try 6, maybe 7. And if I put 6 in my calculator, 6 plus 3 is 9, and then 6 minus 5 is 1, and 6 minus 1 is 5. I'm going to end up getting 1 4/5 for this answer here. All you have to do is plug in 6 into this equation. Put it in your calculator to figure out what the point value is. If I put in 7, it's a really ugly decimal, but that's okay. It's 0.83 repeating. Okay, so I'm looking at 1 4/5 and then 0.8. So 6 is 1 4/5. 6 is 1 4/5. And 7 is 0.8. 0.8, so we're about that. So, and remember, it can't cross the x-axis because I have that asymptote. So this should look something like this. Now, here's where it's kind of interesting. Let's go back to our horizontal asymptote. Because if you clearly see, if you look at my graph, on the left-hand side, this branch in quadrant 2, basically, the branch in quadrant 2 actually touches the horizontal asymptote. That's because this horizontal asymptote is kind of interesting. It's a horizontal asymptote wherever x is greater than 1. Okay? It's a horizontal asymptote for all values of x that are greater than 1, okay, and less than 5. Okay, actually just a horizontal asymptote for anything where x is greater than 1. Because here, okay, once we get past this, these two graphs, the graph right here and this graph right here, cannot touch the x-axis. But this first graph, obviously by mathematical principles, will, because it has an x-intercept. It's kind of a weird anomaly of the graph, but I figured it's hard. So if I did it as an example, I do not think you're going to come up with any of these types of graphs in your homework. You're going to have definitive horizontal asymptotes, definitive vertical asymptotes, and your lines won't cross them. So, but I figured if we did this particular example, you could see how the asymptote could work from one branch, but not necessarily be applicable to the other branch.